Now, here's something that's pretty interesting here. What was going on in that is you had the water filling, and you could try this at home yourself. It's really fun. Make sure that you over a sink, though. Don't make a mess, but just use a regular glass and I don't know, a piece of paper. And as long as no air can get inside, the water can't get out because the air pressure is pushing upwards at 14.7 pounds per square inch. The weight of the water is being pulled by gravity is less than the pressure of the air being squeezed against this side. So since this has a higher pressure, then this can't escape. So here's what we're going to do on this diagram. We're going to need a fair chunk of space here, okay? We're going to use that much, all right? So down here, this is the ground, right? And then here's the house. It's your house down there. And here's you. And I don't know, here's a tree. All right, and then here's a mountain. I don't know, Mount Rainier or something. It's got glaciers on it. So try to make it look kind of like a mountain with glaciers. All right, there you go. So now what we got, we're going to try to draw the atmosphere. And so the atmosphere, of course, has air molecules in it. So we're going to go ahead and put some dots to represent air molecules. And dot, dot, dot. You know, if you want to drive your parents crazy, if they're there, you know, if you want, I don't care. But try to evenly space them. Okay. Now, since we have them evenly spaced like this, it looks nice, but there's something wrong. What's wrong with this picture? How is this inaccurate? Should they all be evenly spaced throughout the whole thing? No, that's right. We should have more down here in the lower atmosphere because the weight of these guys is pushing down and squeezing them together. Air can compress really well. You know, you can put a gallon of air in a cup-sized container if you compress it. You can't do that with water. That's one of the differences between gases, vapors. They can compress, right? Okay, so anyway, we're going to have to put more molecules here. And they're squeezing together. And now since you have more of them flying around and bumping into stuff, there's higher air pressure too. It's the physical bumping of the air molecules into surfaces and stuff that actually represents the pressure because they're bumping and squeezing into each other too. And so what you want to draw is the further down in altitude you are, the closer to sea level, the more air molecules you have. And the higher up in altitude, the fewer you have. Okay? All right, and so now kind of keeps on going forever and ever, going up and up and up. But realistically, we don't have room for that, the exosphere and stuff. There are stray air molecules out there, though. So what we're going to draw then is a little scale here. As you go down in altitude, what happens is you have more air pressure and higher density of the air. More air pressure. And then it's a higher density of the air. Oops, let's see if we can scooch that over a little bit. So here we have more air pressure the further down you go, and the higher the density. Okay? And as you go up in air pressure, it's going to be the opposite. You're going to have less air pressure. And then you're going to have less density. Density, of course, would be how many molecules you have in a given amount of space, right? Okay, so now what also happens is that you go down here, they're bumping into stuff and everything, and they're moving around with a fair amount of speed, and they're transferring that energy, and the name for that energy, there's another name for it. When it transfers it, it's also heat, okay? And so what happens then as you go up in altitude, there's fewer air molecules to be bumping into stuff to transmit its heat energy, this thermal energy. So it gets colder as you go up in altitude as well. All right? Now let's get this definition, what we have here. Remember, density is we already did this, but can you remember what it is? M over V. Okay, density equals mass over volume. Now, here's something I want to mention. When you're down here at sea level, As you go up, you have less air pressure. But the weight of the atmosphere squeezing down on you is what causes it. And how much weight is that? Here's how much it is. Write this down. Guaranteed test question. The air pressure at sea level is 14.7 pounds per square inch. 14.7 pounds per square inch. Okay? You could write that several ways. You can write down pounds per square inch, but there's two ways it's usually abbreviated, like LBS. You know how LBS means pounds? There's another wonderful thing about our system that metric doesn't have to worry about. And then you have a square inch. Right? It's 14.7 pounds per square inch. Or another way you could just do it, they call it also PSI. PSI. Now, pounds per square inch. Air pressure is also measured in millibars. That's barometric pressure. It's another unit of measure for it. And it's also measured in inches of mercury, which was a type of device they use in the barometer to measure it. But for this sake, we're going to say 14.7 pounds per square inch. Okay, so the rule is the higher the altitude, the less weight is pressing down, the less weight of the air, so the pressure and density are reduced. The higher you are in the atmosphere, the less dense the air and the less pressure you have. And that's why it's cold in mountaintops also, and why there's less air to breathe. The air is thin. And if you're climbing up the mountain like Mount Everest, what do you got to take along with you? The oxygen. Something that's pretty cool is that the Sherpas, the people that help them, Westerners make the journey, live in Nepal. They're used to the higher altitude, and so they can breathe better in the thinner air. Now, another thing on the opposite is the lower you are, the hotter it is, and the more dense the air is. And so, what is the hottest place in North America? You guys know this. I bet you learned it in geography class. If you said, what is it? Death Valley, you're right. Because Death Valley, if you drive down into it, it's below sea level. And that's the hottest place on the North American continent. And it's the lowest in altitude. So the air pressure is all around us, squeezing and squeezing.